calculate, but this is just doing recap. Okay. So some proteins might have higher concentration of basic amino acid, would have higher percent nitrogen, therefore their conversion factor will be lower. Okay, so this is where we left off. We did Keldal and Dumas last time. We're going to move on to do other types of analyses. One of the main one is the infrared spectroscopy, which is a secondary method of analysis, and it's used as quality control and online type of measurement, but it requires calibration. That's very important. It requires calibration using official methods of analysis or primary methods of analysis. So what happens here, we measure absorption at either near or mid-infrared. In near-infrared, you are actually measuring the vibrational energy of the peptide bond. In mid-infrared, you are specifically measuring the amide group. So it is very rapid. You don't need any sample preparation as long as the sample is homogeneous, it's ground to uniform particle size, or if it's liquid, then it's liquid sample. The bisynchronic acid assay, or for short BCA, so it's a research method. So we call it research method because you often use it when you have clear solution, where your protein is in a clear solution that does not interfere, nothing in there will interfere with the absorption or measuring absorption. Also, you don't want for these methods to have any reducing agents in your sample, or if you have a reducing agent in the sample, it would be to a certain amount, because this assay is based on the reduction. The proteins reduce cupric ions to cuprous ion under alkaline condition, and then cuprous ion reacts with the reagent, BCA, to give you a color, purple color, that you measure absorption at 560. So if there is high amount of a reducing agent in there other than the protein, then your values are skewed. So it is based on the macromolecular structure of the protein, the number of peptide bonds, because peptide bonds act as reducing, and then the presence of specifically these amino acids, the cysteine, tryptophan, and tyrosine, because they have a reducing functional group. So they have like OH, the tyrosine, for example, and tryptophan. However, cysteine has the SH group. And it's used to quantify proteins in purified solution, and that is solutions that are mostly clear solutions. With BCA, we have to run a standard curve, obviously, and oftentimes our standard curve is formed using BSA, bovine serum albumin, the standard protein. So that standard protein, we measure it at different concentrations, and then we measure the absorption of it, and then plot our linear line, and then get the equation of the line to predict or to calculate concentrations in the unknown. So when we're using research methods, it's always you need a standard curve in order to quantitate. Another research method that is very common is the Bradford dye binding method. And you will be doing this in the lab on the side. So next week you'll be doing Keldal and Dumas for your food products, the assigned food product. But we have 3 stations. One of the stations is just to introduce you to a research method. It won't be part of the lab report, but it will be part of the experience in the lab. And then here what happens is that proteins in general can bind dye, the Kumasi blue dye, changing its color from red to blue. And then you can measure absorption in the range of 465 to 595. The interaction of the Kumasi blue with the protein is based on the amphoteric nature of the protein. That means having the base and the acid in there. It is very sensitive and rapid, but however, it's not for peptides smaller than 4 kilodalton. If it's smaller than 4 kilodalton, it might not react as well with your Kumasi blue. Again, you really need calibration curve, so you will be plotting a calibration curve using bovine serum albumin as your standard protein. Just to remind you, there are many research methods. They are in your chapter in the book. The most common are the BCA and the Bradford, but there's also the Burette and Lowry, and also there is the measurement at 280. Burette and Lowry is also chemical assays where based on reacting your protein with a reagent and then giving you a color and you measure it. So it's another type of reaction, but it's very similar in principle to the other, to BCA, for example. UV light, so we talked earlier last week that we have tyrosine and tryptophan and also phenylalanine. They absorb at 280 because of their aromatic nature. And every protein has to some extent some concentration of this of these amino acids. So every protein can absorb light at 280. So oftentimes it's used for simplicity. You just have your solution of protein, and if it is clear solution, then you can measure absorption at 280. It does follow Beer's law. We still have to do calibration. Again, bovine serum albumin is another very common standard used, but because different proteins might have different concentrations of tyrosine and tryptophan, it would be ideal if you can get the protein standard that is very similar to the protein that you are measuring. If that is a possibility, then that would be great. That would be the most accurate. But oftentimes 280 is used just for comparative between samples, not necessarily to determine an accurate measurement of your protein concentration. It is non-destructive, so that means your sample can be used for something else. So that's very beneficial, especially for research. When you are collecting samples and you really want to use them for something else, you don't want to destroy your sample. So measuring at 280, you can measure and then take that sample and use it again. It's very quick, obviously, but the downside of it, it has to be pure and clear solution. So it's not really used for complex food matrices. Often, if you have peptides, you're measuring peptides and not necessarily entire protein. So these peptides might not necessarily contain tyrosine, tryptophan, or phenylalanine. But you can still use UV absorption measurement. In this case, it's about 220 on average. It ranges between 214 to 224. That's where your peptide bonds can absorb light. Okay, so that's it for proteins. Any questions? So yes.
Do you need the little mic thing for the recording?
You know, my mic ran out of battery and I keep forgetting to change it, but I'm standing by my computer, so I'm using the computer.
I like it. I like listening.
I know, thank you for asking, but yeah, you will be able to hear it. Yeah, I'm not moving too much. I'm just sticking by the computer. Okay, so what I'm going to do is move on to total carbohydrates. We can't send you off that early, in case Zach was wondering. Not even paying attention. Okay. All right. So carbohydrates. So this is the last component in terms of proximate analysis. It's a major component and a very complex component. Let's try to remember our carbohydrates a little bit before moving into analysis. So which of the following is considered carbohydrate? G. Any other answers? Claire?
Is it D, just A and B?
D, just A and B. You are correct. Lignin is not a carbohydrate, it is a dietary fiber. Why is it not a carbohydrate? This is lignin structure. It doesn't have glucoside. It does not have a monosaccharide unit in it. These are the monomers. The monomers of lignin, the subunits are alcohol. They are not a carbohydrate-based monomers. So that is often confusing because lignin is dietary fiber and everybody would think dietary fiber is a carbohydrate. Not every component of a dietary fiber is carbohydrate. Pectin and cellulose are dietary fibers, but they are carbohydrate because cellulose units are glucose. Pectin has galactouronic acid, so there is a galactose in there. So that is why it's considered as well carbohydrate. Okay. Before you answer this, you might not know this anyway, you will know it by the end of the lecture of carbohydrate, but let's define what is starch gelatinization versus starch retrogradation. Those of you in food chemistry, I don't know if you already covered carbohydrate. Who's in food chemistry now? Did you go over carbohydrate or not yet?
Yeah.
Okay. And everybody else has taken food chemistry. So, what is starch gelatinization? Oh dear. Evan.
Is it when like the starch kind of breaks down and forms a gel after it's been exposed to heat?
Okay, swells. So it swells in the presence of moisture and heat, and then it gelatinizes. Okay, and forms viscosity. Okay, that's very in simple terms. What is starch retrogradation? Kind of know.
When it overheats and excretes all the moisture, it breaks down.
Not well. You have like one kind of correct thing in there. It's not necessarily overheat. Actually, when you cool down. So after heating and gelatinization, the cooling and then recrystallization of the starch. So they realign and crystallize. And like staling of bread is due to retrogradation of starch. The pasta formation and the hardness of the pasta, some of it is not just due to protein, but also due to retrogradation of starch. So you have gelatinization that occurs upon heating, and then when you cool down, over time, the starch molecules, the amylose, amylopectin, realign themselves, crystallize, and form a retrograded starch, which is not digestible. It is considered a resistant starch. Okay, let me ask you, what are the four different types of resistant starch? I'm going to tell George. It's like, what are you teaching these kids? Oh, not just George. I'm going to report George to the department head. Just kidding. I won't do that. Oh gosh, I'm recording this. I would never. Okay. So what are the different forms? Oh gosh. And I have about 29 students in this class that can go report me. Okay. What is resistant starch? You know this. Well, we said retrograded starch is resistant starch. Please, one of you can answer this. Where's Alex? Alex is not here today? What? Okay, I'm going to go for Allie.
I just remember that there's 4 types. But
Oh, okay. Okay. Chemically modified starch is the type 4. The type 3 is the retrogradated starch. The type 2 is the starch that has not been cooked, the uncooked starch. And then the first type is the physically not accessible starch due to the matrix. So not accessible but the amylose. So these are your 3 different types of resistant starch. Okay, so but back to this question, from just looking at it, you have starch gelatinization and starch retrogradation. Do you think you can have one method that can measure both? The amount of both? Either or? Evan says yes. You are right. I was hoping for you guys to say no. And then I tell you no, yes. Okay, so it is yes, and then we will talk about the method and see how we can use one method to determine either the amount of gelatinized starch or retrograded starch. But keep in mind, gelatinized starch can be hydrolyzed by amylase, okay, can be digested. Retrograded starch cannot be digested, and that's the basis for that method that we're going to talk about. All right. Importance of carbohydrates. Why are they important? Why do we care for them? Zach?
They provide energy.
Yes, excellent. They provide energy. Of course. And then second, what component of carbohydrates is really important for health?
Fiber.
Yes, dietary fiber. Okay. Not including lignin, since lignin is not a carbohydrate, but it is a dietary fiber. What other properties do carbohydrates have in food, and why do we care for those? What's the function of starch in food? In some foods? Capstone groups. Why would you sometimes add starch to your formulation?
Gelatination.
Gelatinization, viscosity, body building. That's kind of like texture. So stabilizing emulsion, stabilizing the foam. So if you have your bread, for example, it's not only the proteins that is going to give you the air bubbles and the volume. If there's no starch, there is no matrix to hold these air cells in place. So starch gelatinization is very important in different applications due to the structure and functionality it brings to the food products. Okay, other than that, you all know the Maillard reactions. So carbohydrates, especially reducing sugars, play a role for flavor and color development in the presence of proteins. Preservatives, right? Sometimes sugar, here I can put that in. So sometimes sugars are added to lower water activity. I don't even know what. Would anybody use this nowadays? Okay, so lowers water activity, so it's basically kind of a preservative. And we talked about resistant starch that are not susceptible to digestion. So if you have a food product with a high amount of resistant starch, then you will, if you're prone diabetes or you have diabetes, this would be good because it won't give you a high glycemic index. So pasta, for example, is better for diabetic people than rice or potato because in pasta you have retrogradated starch. Okay. So what's the importance of analyzing carbohydrates? The common theme that you all pick up on is why is it important to analyze? Why do we care? We don't care about carbohydrate? Okay, off you go. Have a happy weekend. Nobody's gonna leave? Okay. Since you don't care about carbohydrate analysis. Okay, I give up. No, I'm not giving up. Go ahead, Allie. Hold on.
Nutrition labeling?
Yes, for dietary fiber and for sugar. You can say that. Okay, here we go. Quality control. So determining the amount of carbohydrates during processing in the end product to authenticate the ingredient, to assure consistency in the quality of your end product. Research. Oftentimes, let's say, I give you an example that we do very often in our lab, is we glycate proteins. We bring a protein and we react it with a carbohydrate to enhance the functionality of the protein. But at the end, I do not want to keep any free carbohydrate in my mixture, in my protein that is glycated. So after glycation and after purification, I go back and analyze carbohydrate in my sample to determine whether or not I have excess carbohydrate that has not been linked to the protein. So that's one example. Definitely there are many other examples of research where you really need to quantitate your carbohydrate, your dietary fiber, specifically the sugars, and then product development as well. When you're producing a new product, you want to determine whether did you end up gelatinizing the starch, did you end up retrogradating the starch, is the amylose to amylopectin ratio the ratio that you want for your texture. For example, amylose retrogradate faster than amylopectin. So for an application such as pasta, you want higher amylose to amylopectin. But for bread, amylose retrogradate might cause your bread to stale faster, so you want lower amylose to amylopectin ratio. So looking at amylose to amylopectin ratio is always important for your end product. That is one example. Okay. So very simple classification before we get started with analysis itself. So in carbohydrate, we have monosaccharides, di and oligosaccharides. Di, of course, is 2 units, oligosaccharides 3 and higher, up to 10 units, and then polysaccharides, you have the starch and dietary fiber. So starch, for example, is a polymer of glucose, and disaccharides could be 2 glucose, like galactose, like glucose and fructose, like sucrose, glucose and galactose, like lactose, etc. So the different subunits that are there will indicate what type of carbohydrate you have. Okay, and then in analysis, we either analyze monosaccharides, like we are interested to look at amount of glucose per se, or we're looking at disaccharide, maltose, or lactose, or sucrose, or we are after determining total starch or total dietary fiber. And we will be learning about all of these. So like with anything, you have a sample preparation step. Okay. Sample preparation. Before anything, you want a representative sample. Okay? So that is very important for any analysis to start with a homogeneous lot and a sample that is representative of the population. From there, you want to remove moisture and you want to remove fat. These will interfere in the extraction of carbohydrates and the analysis of carbohydrates. So drying, often vacuum oven is used because if you remember from your moisture lab, we talked about vacuum oven causing the least degradation. So high carbohydrate food in, for example, the air draft oven will be subject to degradation, burning of the sugars, Maillard reaction. So we don't want that. So we try to do mild drying. Often it's vacuum. Sometimes if you have a freeze dryer available to you, then that would be another form of drying. Then you want to remove the fat, and oftentimes it's solvent extraction. Very often if you have Soxhlet, you go with Soxhlet. If not, you do batch extraction with solvent. So now your sample is dried and it's fat-free. What you have in there is your carbohydrate and proteins left. So what you're going to do in the lab is a total carbohydrate assay. And this total carbohydrate assay is basically done on samples that don't have, let's say it's not a complex matrix. So you'll see that you'll be doing them on beverages in the lab. Liquid samples that have high carbohydrate but not necessarily dietary fiber. Because dietary fiber, say pectin, cannot be analyzed by this method. So it is basically for monodisaccharides. You can do starch as well. So, or cellulose can be analyzed by this method, but it has to be a simple matrix, simple food matrix. And it will give you an estimation of the total carbohydrate, but this is not an assay we use for labeling, because it won't be determining all types of carbohydrate. Okay, so the method we're using is phenol sulfuric acid method, and the principle of it, from its name, there is a phenolic substance that you're going to use and sulfuric acid. We're going to use a highly concentrated sulfuric acid, and what it will do, the high amount of sulfuric acid once you put it with the sample, it generates a heat right away, and that heat that is generated, it's going to cause glycosidic linkages to be broken. So it will break glycosidic linkages into monomers. So you will be producing monosaccharides. Okay. So the monosaccharides, they are still there in your tube, and you still have a strong acid, and you still have heat that is generated from putting the acid with the food. It's an exothermic reaction. And then what happens is your monosaccharides are going to go through enolization and dehydration reaction to give you furans substances. So these furans then will be the compounds that will react with a phenolic substance. So here's a furan and here's a phenol. They will react to give you a compound that will have an absorption between 480 and 490. So obviously, since you have an absorption or a reaction that provides you with a compound to measure absorption, in order to quantitate, we need to convert absorption to concentration. And by do so, you will have to plot a standard curve. And usually what you use for the standard curve is the most abundant monosaccharide that would come out of your carbohydrate. So if your carbohydrate is mostly going to be glucose, it makes sense that you have a glucose standard. And that's what you're going to use in the lab. Glucose standard will be used. The potential disadvantages of this method is that if you have high amount of fructose, for example, fructose react differently than glucose. So it's not a stoichiometric reaction. So it's not necessarily based on quantity. Absorption is not based on the quantity of the reactants. No idea. Okay, so lost my thought. what was I saying? Non-stoichiometric reaction. So basically, if you have fructose, it will react differently than if you have glucose. So in order to quantitate and to quantitate accurately, if you know the mixture in your sample and you know the different composition, it would be great to have similar ratio of, let's say, glucose to fructose in your standard. So when you prepare your standard, you try to prepare similar ratio of those monomers that you would expect your sample to have. Okay. Yeah, I don't think I have anything else to say about this method. You're going to be doing it in the lab, not next week, the week after. Any questions? No? Okay. Moving on to measuring specifically mono and oligosaccharides. To measure mono, di, and oligosaccharides, there are so many different methods that we'll be talking about. We categorize them into 3 different categories. We have the colorimetric method that are basically based on reducing cupric to cuprous. So they are mostly for reducing sugars. And then the chromatographic method, so you can do the screening with paper and thin layer chromatography, or we can do quantification with HPLC and GC. And then there are the enzymatic methods, which are kind of like bread and butter for carbohydrate, because to determine total starch and total carbohydrate, total dietary fiber, for example, it's really heavily based on enzymatic methods. Okay. So if you have a food matrix, right, it has a lot of different things in it, not just your mono and disaccharides in pure solution. So you have your water, your moisture, your fat, your protein, your carbohydrates, total carbohydrates like polysaccharides, and dietary fiber. And all what you care for is just determining the mono, di, and oligosaccharides in your sample. So you really want to get rid of everything else to purify your sample. So what you would do first is, like we said, homogeneous sample. You dry it, you defat it. Okay, so we got rid of moisture, we got rid of your lipids, and now we have polysaccharides, proteins, and your monodisaccharides. So you want to get those out, separate them from protein and polysaccharides. So what you would do is you would mix your sample with 80% ethanol. And if you see here in this picture, so you have kind of a hot water bath, not necessarily directly on a hot plate, but a water bath where you put your sample with 80% ethanol and you do the extraction for a certain period of time. What you see here, there's a distillation unit. So you have water running through cold water, so your ethanol is going to evaporate and then condense. The reason we have that is because ethanol can evaporate really fast and then not get the extraction done. So what you do is you make it more efficient. Like if ethanol evaporates, it condenses back into your sample. So after a certain period of time, you take your sample, and now what you have is you have your mono and disaccharides are soluble in the ethanol, and then polysaccharides and proteins are insoluble, so they precipitate. You either let them sediment, or you can have a centrifugation step to get that ethanol, 80% ethanol, separated from your polysaccharides and proteins, and it contains your mono and disaccharides. So Now you have your mono and disaccharide, but they are in 80% ethanol, and that might not be compatible with the method of analysis you're going to follow. So basically, why many people are missing? How many people are missing today? Is there like a test or something? It seems like the room is empty. 6? Wow, what's going on? Is there anything going on? It's just a Friday? Okay. So it's empty and the rest of you are almost going to fall asleep. So not very encouraging to teach. Should I just quit? No? Okay. Thank you, Nathan, for the encouragement.
Yeah. Go. You got it.
Okay. Do you want to teach?
No, I'm not good at it.
Okay. All right. So, so now we want to get rid of the ethanol because it might not be compatible with your method. So what we do is we use a rotovap. I don't know how many of you is familiar with a rotovap. Oh, you've seen it in the isoflavone lab. Okay. So basically you have water bath. You regulate the temperature. You put your sample in a round bottom flask, and then you apply certain you build a vacuum by vacuum pump, and you have a condenser here linked to cold water, and what happens is your ethanol will be heated and goes up to the condenser, but instead of condensing back into the flask, condenses into another collecting flask. So you will have your solvent here, and then you will have your dried out sample. You take that flask that has your dried out sample, and then you reconstitute it with whatever is the solution that will work for your assay. Often it's just water, or it could be a buffer, or it could be another solvent, another organic solvent. So when you do that, then if you want to purify it even more, because sometimes you have free amino acid, organic acids, other components that you really don't care for, colors, for example. So sometimes you pass it through a cartridge. That cartridge basically is kind of like a small chromatography cartridge that has an ion exchange that will pick up all of these ions that you really don't care for in your sample. So you kind of clean it even more. And then you have a purified sample ready for analysis, whether by the colorimetric assays, or by chromatography, or by enzymatic assay. So another type of treatment to kind of purify or extract your mono and disaccharides, we call it a Carbohydrates treatment. It's basically a Carbohydrates reagent that has certain components, for example, potassium hexacyanoferrate solution with zinc sulfate in it. What happens is it kind of breaks any emulsion. If you have any residual fat and you have protein and you have aqueous solution, you might form an emulsion, but it breaks it, and it precipitates proteins and polysaccharides, and then what remains in your solution, and also it absorbs colors, what remains in solution are your mono and disaccharides. So this way is another way to clarify, but the most common way, the solvent extraction, is more common than the Carbohydrates treatment. It's mostly used. Your question.
So then, what would be the benefit of using correct?
Well, you know how when people develop methods, they tend to develop multiple methods, and whatever your lab is familiar with, they would go with. Yeah. So for everything, there's many ways of doing things, right? Okay. So I think this is a good stopping point for next time, to start with the actual methods of analyses for mono and oligosaccharides. So off you go. Happy weekend.